Chapter 11, Section 4, Ensemble Learning. This section covers ensemble learning, an advanced machine learning method that can be used to achieve higher prediction performance than traditional methods. Ensemble learning is a method that combines multiple machine learning models to achieve higher prediction performance than could be achieved by a single model. The topic of this chapter is classification, but we can use ensemble learning not only for classification, but also regression. There are two methods of ensemble learning, bagging and boosting. Here, let me focus on bagging and its representative method called random forest. Random forest is an ensemble learning method that trains and combines multiple decision trees to create a forest-like learning model. In the training phase, the random forest creates multiple training datasets from the original dataset. Specifically, the random forest randomly extracts around 30 to 70% of the data by sampling with replacement multiple times, and use those extracted samples as training sets. Here, the random forest extracts data by sampling with replacements, so a particular observation can be used multiple times. In other words, observations included in each training set are different, but can be overlapped. Then, the random forest creates multiple decision trees, and each decision tree in the random forest selects not all but only some of the features and uses them as predictor variables. We should know that here each tree selects the features randomly. So each tree uses different set of predictors, and thus each tree will be trained by different set of observations and a different set of predictors. That is, a random forest consists of diverse decision trees. Next, the random forest trains each decision tree, and each tree outputs its prediction result. In classification, each tree outputs predicted class for each case. Since the random forest contains many decision trees, each case has multiple predicted classes from multiple trees. Finally, the random forest determines the output by majority decision. As I said, each case in the dataset has multiple predicted classes from multiple trees in the random forest. The random forest aggregates the predicted classes from the multiple trees and determines the one best class by majority decision. It will be the output from the random forest model. In classification, a random forest determines the output by majority decision, but in regression, the output is determined by computing the average. In this figure, the random forest contains only 3 trees, but in practical cases, a random forest consists of hundreds of or more decision trees. Random forests take majority decision to determine the output. But why does it lead to higher prediction performance? Strictly speaking, for a majority decision to achieve higher performance than a single model, two conditions should be met: diversity and acceptability. The first condition, diversity, means that each tree outputs different outputs. And the second condition, acceptability, means that each tree should have a certain level of accuracy rate, specifically greater than or equal to 50%. Let's look at the first condition, diversity. Suppose we have 5 trees and each of them answer the 5 questions. The answer should be 0 or 1, and the correct answers are written in the first row. Suppose the trees output the same answer. That is, there's no diversity. The cells shaded with orange color represent cases where each tree gives the right answer. Here, there are 5 trees, so as a majority decision, the answer that 3 or more trees gave will be adopted as the conclusion. In this case, all trees give the same answers. So, the conclusion of the majority decision will be exactly the same as that of each tree. This principle holds even if the accuracy rate of each tree changes. So, the majority decision is not worse than the decisions by each single tree, but no better than that. Therefore, majority decision is not meaningful. Next, let's look at the second condition, acceptability. Suppose the first condition, diversity, is already met. That is, each tree gives a different set of answers. Let's look at a case where we have diverse trees, all of which has 60% of accuracy rate. In this case, if we take the majority decision, the accuracy rate becomes 80%. It is better than each single tree's accuracy rate. Next, let's look at another case where all trees have 40% accuracy. In this case, the accuracy rate of the majority decision is lower than that of each tree. Therefore, a random forest is not always a better model than a single decision tree. If the random forest consists of trees with insufficient acceptability, its performance will be lower than a single tree. So, even when we use a random forest, we should have training data that contains sufficient information to develop a decision tree with a certain level of acceptability. Thank you for watching. Please thumbs up and subscribe to my channel.